So as you can see that delta mu, or the chemical potential difference, is in the last lecture as I was discussing, is a function of the chemical potential difference delta mu here is a function of the driving force, right? D equals to minus delta mu, right? So driving force is minus delta mu, and delta mu is a function of T and P. And as you can see, when I simplify, I take delta Cp, which is the heat capacity difference between alpha phase and beta phase. So I am considering the alpha to beta transformation. I'm just giving a quick reprise. And then also there is this delta S0. Delta S0 is the difference in entropy at the standard state. Standard state is defined by zero, superscript is defined by our transformation temperature. Transformation temperature is the temperature at which alpha and beta are in equilibrium. And also there is T minus Tr, right? There is T minus Tr, and this TTR basically is the transition temperature. This is the transition temperature at which alpha and beta are in equilibrium, right? Alpha and beta are in equilibrium. When we write alpha and beta in equilibrium, we use this symbol, reversible symbol, right? And you have also, when you did the algebra, you could get delta Cp, TL and T by Tr. Now, if you see delta T is T minus T TTR, or T minus T transformation temperature, means there is the transformation temperature. So this is TTR, which is the transformation temperature, and this is some temperature away from the transformation temperature. But if delta T is small, then this ln term can be approximated further. So for example, I can write T minus Tr by Tr. So T minus Tr by Tr, if I do, then basically I can write this ln 1 plus delta T by Tr, and then it's the logarithm, and this is very small. So basically I can expand on expand this logarithmic series about this delta T by Tr, means TTR, T, and the subscript is Tr, right? So TTR, which is the transformation temperature. So delta T is means how far away is my temperature from the transformation temperature. Now if this delta T, that is the deviation from the transformation temperature, is small, then I can use this ln 1 plus delta T. So basically T by Tr is written as 1 plus delta T by Tr, T is Tr, and then basically I am taking only the first power of it, right? And so basically the first power is delta T by TTR, and right, T transformation. So delta T by T transformation, and so that's what I have done. So I can remove the ln part, right? And you have the delta Vm0, that is again 0 basically denotes the standard, that is the standard, means the standard state here, the standard state here is taken to be the transformation temperature TTR and say some P0 is the standard pressure. P0 can be 1 bar, 1 atmosphere, whichever you want to. So you can take some P0, and you can take the transformation temperature itself, right, to define the standard state or the 0, right? It's the if you look at the superscript 0 stands for transformation temperature and P0 pressure, right? Now as you know, delta is 0, that is the difference in entropy of alpha and beta, between alpha and beta, difference in entropy between alpha and beta in the standard state is related to the difference in enthalpy by the transformation temperature TTR, right? So, and as we know that, we can basically write this, as I told you, that we have taken only the first term. So basically ln 1 plus x is x plus x square by 2 factorial plus so on, but I am taking only delta T by T transformation, because delta T by T transformation is very, very small, because the difference, the delta T that I am taking is delta T is really, really small, right? So it's a very small deviation from the transformation temperature. So as a result, delta T by T transformation is very small, right? We can only take the we can take the first order term, right? First order term is the power 1, right? So this is what I have done, and if I take that, I can simplify further. That's what I was telling, simplify further, and then, and if I simplify further, I already have a delta T here, and here again Tr minus T is delta T, but there is a minus sign because T minus Tr is delta T. So Tr minus T is minus delta T. So this becomes delta T whole squared by the transformation temperature T. Remember, this is Tr. So this is something. So it is Tr is the transformation temperature or the temperature. Sometimes Tr can be replaced by T boiling, but Tb, which is basically the boiling point, which is basically the equilibrium between the liquid phase and the vapor phase, or it can be melting point, which is the equilibrium between the solid phase and the liquid phase. So in this way, I can basically write delta mu as a function of delta H naught. Delta H naught is the enthalpy of transformation, difference in the enthalpy of transformation, right, at the standard state, calculated at the standard state, and the difference in heat capacity, right, there is a difference in heat capacity, and then there is this delta T, and this is T transformation, right. So, and then there is also delta Vm0, delta P, right. So, this is how we can calculate delta mu, and from delta mu I can calculate the driving force, because driving force is proportional to delta mu. Now, I will come to a very interesting concept, which is called order of a phase transition, right? Order of a phase transition. Again, I am considering a phase transition from alpha to beta or beta to alpha. Beta can be the liquid phase, alpha can be solid phase, right? Alpha is, say for example, alpha is solid, beta is liquid, then the phenomenon that we are talking about is melting. Again, if it is alpha is the liquid phase and beta is vapor phase, then the phenomenon that we are talking about is boiling or evaporation. Okay, or alpha is solid and beta is say vapor, then it is like we are talking about sublimation. So now, as you can see here, mu beta represents the molar free energy of the beta phase for a unary system, right? Mu beta represents the molar free energy of the beta phase for a unary system, and mu alpha denotes the molar free energy of the alpha phase for a unary system. Now, if you see del mu beta del P minus del mu alpha del P is nothing but molar volume of beta, the difference in molar volume of beta between molar volume of beta and molar volume of alpha. Molar volume of beta can be more or less than the molar volume of alpha, and that we can think of delta Vm, and this delta Vm at the transformation temperature, right? So this is like a delta Vm due to transformation. So this is delta Vm due to the phase transition that has taken place. So delta Vm with a superscript here, I am indicating that. Similarly, I can look at the variation of this molar free energy with respect to temperature. So for each phase, so you have del mu beta by del T as at a fixed pressure minus del mu alpha by del T at a fixed pressure, which is nothing but minus Sm beta plus Sm alpha, which is again delta Sm transformation or delta Sm transition. Now this delta Sm is again related to the enthalpy of transformation, that is delta Hm, the molar enthalpy of transformation divided by the transition temperature. So this is the transition temperature. This is the enthalpy of transformation, that is the heat that is means absorbed or given out during transformation from one phase to another. Now, as you know that the delta Vm transformation is not equal to 0 whether you are considering melting, vaporization or solidification. Similarly, delta Hm transformation is not equal to 0, right? All of these are not equal to 0, right? So if you look at that, you will see one very interesting point, means when you plot them, for example, volume, if I plot volume versus temperature, now you see this C is like the alpha phase. So Tm is your melting point. Tm, so I am telling Tm is your melting point. So I am talking about a melting transition or a solidification transition. So Tm can be defined as the melting point or freezing point. You can also call it freezing point. Now if you see, this is your molar volume before transformation, right? This is the alpha phase. This is your alpha phase, and this is your beta phase. And see, at this transformation, what has happened is that there is a delta Vm which is non-zero, right? This is delta Vm Tr, right? This is the delta Vm melting. Okay, so basically this is the delta Vm transformation or delta Vm melting. It is better to write delta Vm Tr. So this is not zero, but you see a discontinuity here. So you are seeing a discontinuity in the volume. Okay, you are seeing a discontinuity in the volume when you go from, when there is this transformation. So this is the alpha phase and this is the beta phase, or you can think of this as the solid phase and this is the liquid phase. And as you can see that there is a jump, right? There is a jump at the transformation temperature or the melting point. Similarly for enthalpy, so for enthalpy, see for example here, so from some temperature at start, now in this case what I am talking about is like it is like a delta H equal to Cp dt. So here we can think of this as Cp dt. Now once you have reached the melting temperature, there is no sensible heat, there is no Cp dt, there is no rising temperature, right? So basically what has happened is you are at Tm, but now you are changing the phase, that is from solid. So this is say for example Cps. So if I think of this is basically Cps, that is solid phase dt, and this goes up to the transition temperature. Now at the transition temperature again there is a jump and you get say Cpl, right? So you see here the first derivative of chemical potential, right? The H is or Vm or delta H. These are all first derivatives of the chemical potential or first derivatives of the molar free energy, and those are discontinuous. Those show discontinuity, right? So basically, if you think of this is the solid phase, then this is Cps dt until the transformation temperature. Then there is a jump, and that jump is basically delta Hm Tr, which we also call as latent heat, right? Latent heat of transformation or heat of transformation. And then you have Cpl Cpl, right? So look at the enthalpy here. So if you see here, I am taking that it is a Cps, and here it is so basically the enthalpy is increasing, right? So for example, liquid has more heat content because liquid freezes to solid, then it gives out heat, right? If liquid freezes to solid, so we can easily understand that the liquid phase will have more enthalpy or heat content than the solid phase. However, if you look at the chemical potential of the free energy itself, only thing that you see is that it varies as a function of temperature this way, but the slopes are basically corresponding to, this corresponds to say Sm alpha, this corresponds to the slope here corresponds to say Sm minus Sm alpha, and this is minus Sm beta, right? So basically, and again this is S by, now if you look at the entropy, now if you look at the molar entropy Sm, let us call it Sm, then again you have this discontinuity, right? This is the entropy of transformation, right? So where the first derivative shows this discontinuity, the first derivative of the molar free energy or first derivative of chemical potential shows jump, then those transformations are called first order transformations, right? Those transformations are called first order transformations. Now, first order transformations, example, melting, solidification, vaporization, right? So these are so these are all examples of first order transformation, where you will see later there is a theory called Landau theory, which I'll talk about in the later, much later, and there also you can see a further discussion on this first order transition compared with first order transition and second order transitions and higher order transitions. Now, if you look at the first order transition, what I told, first derivative of the fast derivative of the molar free energy or fast derivative of chemical potential will be discontinuous, right? As you can see that Sm, if you look at the change in Sm, if you look at the change in Hm, or if you look at the change in molar volume, you will see that there is a fast derivative. These are fast derivatives. Molar volume is fast derivative with respect to pressure, enthalpy or entropy, fast derivative with respect to temperature. So these show discontinuities. Now what about Cp? Cp, as you know, del S del T is Cp by T. So Cp will show, so at the discontinuity there will be a very sharp rise in the heat capacity, right? It will basically go as very large value, right? There will be because this is a discontinuity, so it basically goes to as high as infinity, right? So there is a very large Cp at the transition, so there is a very large change, a sudden shoot up in the heat capacity at the transition temperature, here the melting point. So here if we look at melting points, then Cp goes very high. As you can see here, the Cp is varying like this, and then suddenly it shoots up like this, and then it comes back and it follows this. So at the melting temperature, you can see there is a Cp is the second derivative, right? This is the second derivative. We have shown that, right? Del, for example, del mu del T is minus S, and del S del T is basically Cp by T. So del 2 mu del T square equals to, this is something that we have discussed, that del 2 mu del T square is basically going to be, so if I look at del mu del T, P is equal to minus S, and del 2 mu del T square at constant pressure equals to del S M, again I can think of this as Sm, del Sm del T, which is equal to Cp by T, but there is a minus, so this is basically, this is a minus sign, right? Del mu del T is minus S, so this is minus Cp, right? There will be a minus sign here. This is something that we have shown earlier also. So do not forget the minus sign, because there is a minus sign here, and as you know, del Sm del T, del T temperature, T is here, capital T temperature is no, and at constant pressure this is equals to Cp. Cp is molar heat capacity by temperature, right? So basically del 2 mu del T square again at constant pressure is minus of Cp by T, right? So and at T equal to Tm, as you can see, it basically shoots up, right? It shoots up to a very large value. Now if you look at second order phase transition, so second order phase transitions are not means it's not like melting, or melting is not it's a first order transformation. Then evaporation is a first order transformation, sublimation is a first order transformation, but second order is like conducting to superconducting transition. So if you think of conducting to superconducting transition, this is an example of a second order transition. What is a second order transition? The volume versus temperature. If you look at volume versus temperature, you will see that the fast derivative is continuous. Fast derivative is continuous, right? It is continuous here, right? As you can see here, it goes here and then it goes up. Similarly, there is a change, but it is continuous, right? So the enthalpy is continuous, right? Molar enthalpy is continuous. Chemical potential, as you can see here, it varies this way, very continuously. So which tells you that the fast derivative, the slope is this tangent. This is also continuous, right? So entropy, for example, the change in entropy is continuous. However, if I look at the second derivative, it shows discontinuity, like Cp shows discontinuity. So Cp, there is a discontinuity. So in second order phase transitions, there is a discontinuity in the second derivative of chemical potential or molar free energy with respect to temperature, right? So if you can see here that the second derivative shows clear discontinuity, and that corresponds to delta Cp, right? The Cp of the superconducting state and Cp corresponding to the normal conducting states, right? They are basically different. There is an abrupt jump there. But there is no abrupt jump, for example, in entropy of transformation or molar entropy of transformation or molar enthalpy of transformation or volume of transformation, right? There is no abrupt change there. These are continuous. But CP shows a abrupt change, right? CP, as you can see here, by the nature of the slope, that the slope changes, right? Slope changes from one point to the other point. So there is a change in slope, but although there is a change in slope, it is continuous. But CP becomes discontinuous because of this small kink here, right? If you see the kink here at the transformation temperature, or small change here, this change itself is sharp. So since it is sharp, since this change is sharp, that leads to discontinuity in CP, and that is what characterizes second order transformation. So some ferroelectrics also show this paraelectric to ferroelectric transformation that are of second order, right? So there is yet another transformation. Ren first basically classified it. So it's called a lambda transition. It's called a lambda transition. In lambda transition, for example, it is like a cubic. So basically, you have a cubic crystal. Then cubic crystal means crystal with cubic symmetry. It undergoes symmetry breaking and becomes a tetragonal. Means it becomes a tetragonal crystal. That is, there is a symmetry breaking in terms of the crystalline symmetry has broken to tetragonal. From cubic, it has broken to tetragonal. Right? One of say cubic, for example, has 3 4-fold rotations, but tetragonal will have only 1 4-fold rotation, right? So basically there is a symmetry breaking, and this type of symmetry breaking transition often is called a lambda transition, because although the first derivatives are continuous, the CP shows the change in CP mimics very much of the first order transformation. So it goes very high, it goes to infinity at the transformation temperature. It goes very high. The CP abruptly changes to very high value. Means basically CP approaches infinity at t equal to t lambda, and then again it falls back, right? So and it shows this lambda like appearance, right? Lambda basically is represent this way, right? This is how we write lambda. So this CP follows this lambda type of a curve where there is a shoot up at the transformation temperature. So we can basically now use this information. So basically for unary systems, using this unary system thermodynamics, we could classify different types of phase transformations or phase transitions, right? So for example, first order transition, which is like melting, evaporation, etc. Then there is this conducting, superconducting transition, which is a second order transition, where the second derivative is discontinuous. And then there is yet lambda transition, where first and second derivatives need not be discontinuous. However, lambda transition is a very special type of transition where CP, although the first derivative is not discontinuous, CP shows behavior which is very much similar to that of the first order transition. Okay, so how does the chemical potential change? As you can see that, for example, below Tm solid. So if you look at the solid curve here, this is your solid. And then this is your liquid. So liquid has a higher energy, gases even higher energy. So solid has the lowest chemical potential, or solid has the lowest molar free energy, and therefore solid is extant. Then beyond Tm, liquid becomes the lowest energy state, right? Liquid becomes the lowest energy state, and you go further above boiling point, gaseous state becomes more and more favorable, right? So basically, as you know, del mu del T equal to minus S or minus Sm, right? And S gas is greater than S liquid, and S liquid is greater than S solid in general, right? So all this basically, as you can see, the slopes, also from the slopes you can see that S gas is much steeper than S solid, for example, right? So if you characterize the slopes here, this is one slope, this is another, and this is the other one, and it's very, very steep, right? So this is changing chemical potential. So I have, just for simplicity, I have drawn with approximated them using straight lines. Now think of melting as a function of applied pressure. So you can see now, if you know this change in chemical potential or change in molar free energy as a function of pressure at constant temperature, which is equal to molar volume. Now think of different cases. Say for example, when you have, this is your mu solid. Now see, I have drawn a parabola here, and I am also approximating with it a slightly curved, it's like a parabola, right? So this guy and this guy basically represents, so this mu solid is this one. So basically below Tm, solid has a lower chemical potential or molar free energy than the liquid, right? Now let us assume that Vm liquid is greater than Vm solid. Now if Vm liquid is greater than Vm solid, and you know del mu del Pt, which is the slope, is equal to Vm. Now Vm liquid is greater than Vm solids, right? So basically, if you look at that, if I change the pressure, for example, so I am increasing, so this is my Tm, this is my original Tm at say 1 bar. Okay, the yellow lines correspond to these yellow lines, basically these lines, these ones, this one and this one, or this temperature corresponds to some pressure. But now if you think of this, if Vm liquid is greater than Vm solid and the del mu del P at a fixed temperature, for example at a fixed temperature, will be Vm, and Vm liquid is greater than Vm solid. Now as you increase pressure, the shift in the liquid free energy or molar free energy will be much greater than that of the solid, right? Because Vm solid is smaller than that of Vm liquid. So with increasing pressure, so this is like increasing plus delta P with increasing pressure, right, plus delta P, you will see that the solid energy, that is the solid guy, the solid free energy will shift much less, right, because Vm solid is small compared to the liquid. Now if that is so, if I again draw this, so if I again try to intersect them, because the intersection point is the point where they have equal chemical potential, that is mu solid equal to mu liquid. So that marks the transformation, and that gives me the transformation temperature. Now you see, if I increase pressure, then this curve shifts to the right, the intersection point shifts to the right, it is shifting to the right. That means with applied pressure, melting point will increase if Vm liquid, that is the molar volume of liquid, is greater than that of solid. Molar volume of liquid is greater than that of solid, then the change in energy or change in chemical potential will be much steeper for the liquid than that of the solid. As a result, the melting temperature or the transition temperature will shift to the right, to the right of the original melting temperature. So as I increase pressure, it will shift to the right. So it will melt at a higher, means so basically the solid will melt at a higher temperature. Now if the solid will basically, this melting temperature increases means solid will basically melt at a higher temperature. So solid retains, means it retains its solidity, means it remains solid till means it remains solid beyond Tm, right? So if there is an increase in pressure. On the other hand, if you think of, so this is the point. So if you look at this, now this is molar volume of solid and this is molar volume of liquid. Now I am thinking of molar volume of solid to be greater than that of liquid. Now think of one common example where molar volume of solid can be greater than molar volume of liquid. If molar volume of solid is greater than molar volume of liquid, what does it mean to density? Okay, and we have done this example. So please try to, so this ice water transformation. So carefully have a look at it and see this very interesting phenomenon. See here, this mu, this is again the molar free energy or the chemical potential that is plotted along the y-axis against temperature. Now if you see here, the volume of solid, right, here the volume of solid, molar volume of solid or volume per mole of solid is greater than that of liquid. As a result, the solid shift, that say for example this is my original curve, okay, original solid free energy or solid molar free energy. But now because the molar volume of solid is much higher than that of the liquid, now with an increase in pressure, if I have some pressure, then the solid free energy will shift to a much higher value, right? Solid free energy shift more and the liquid free energy will shift only slightly, right? This is the original liquid. So this is this yellow line represents the original liquid free energy curve, and this is the slight change in the liquid free energy curve as a function of pressure, right? If the pressure is increasing this way, then that for each temperature, right, del mu del P at each temperature, basically it will give a much smaller rise than the solid. So if that is so, now if you look at the intersection, the original intersection was here, now the intersection has shifted here. So original intersection was at this temperature, now it has shifted to this temperature, right, this temperature. So this at this temperature, so it has shifted here when it was originally here, right, when there is an increase in pressure. So if the molar volume of the solid is greater than that of the liquid, then the melting point is depressed or melting point decreases with increasing pressure. If I apply more pressure, the melting point will decrease, right? So this is very interesting, very simple thing, but you just have to apply your logic and you can understand that. And remember, when I am talking about mu, the slope is what is changing, right? The del mu del Pt, that means at a fixed temperature, the derivative of the chemical potential as a function of pressure is the molar volume, and that molar volume basically, that means if you have a mu versus T curve, then at each T, at each T, if you have a mu versus P curve, then the slope basically, if you have a mu versus P curve, then the slope basically gives you Vm. But here at each T, think of this, that the solid has more molar volume than liquid. So as a result, the solid curve will shift more, right? Because see, this is where, say, although if I draw mu versus P, then molar volume is a slope. However, when I am drawing mu versus T, then at each temperature, right, at each fixed temperature, there is a change in molar volume. If molar volume of solid is more than that of liquid, obviously the magnitude shift of the solid will be much more than that of the liquid. And immediately you can follow that at any temperature, if that happens, then basically the original intersection point starts shifting to the left. Right? This is a very interesting and very interesting conclusion of the discussion and of the property, right, that change in molar volume with respect to pressure at any given temperature is equal to the molar volume, and if the molar volume of solid is greater than that of the liquid, think of what is the relation between densities. Again, density, see, if you have a single component system or a pure system, then your molecular weight remains the same, and molecular weight by molar volume basically gives you density. So now if molar volume of solid is greater than that of liquid, is the solid lighter than liquid or not? And if that is so, then in such a case, how will the melting point change as you increase pressure, right? And the pressure increase is given by these arrows, right? So you can see the pressure increase is indicated by how much the free energy or how much the molar free energy will shift, right? The molar free energy will shift slightly here for liquid because VML is much smaller than that of solid, right? And as you can see here, that's why in such a condition, the Tm shifts to the left, right? So for example, think of this example quickly. Rho ice is 0.917 and rho water is 0.999. So as a result, if you look at this, Vm is now m by rho. Now if you if you look at the delta mu of ice, then delta mu of ice, basically you have del mu del Pt equals to Vm, and delta P, here I am taking 2 bar and 1 bar. Temperature I have taken as 0 degrees Celsius. Pressure is increased from 1 bar to 2 bar, right? Pressure is increased from 1 bar to 2 bar. So basically the delta P, the change in pressure, is 1 bar, right? Which is basically 10 to the power 5 pascals. And del mu del P at any fixed temperature is equal to Vm, and Vm is calculated from m by rho. So now delta mu, right? Delta mu by delta P at any given temperature is equal to, so it is at 0 degrees Celsius we are looking at. So del mu by del P is equal to Vm, right? So del mu ice is basically coming out to be 1.97 joules per mole, and that of water comes out to be 1.8 joules per mole. And if that is so, you find out what happens to the melting temperature, right? Delta mu ice, that is the change in ice, is the change in chemical potential of ice is 1.97, while that of water is 1.8. So water basically increases slightly, while ice changes by a lot of amount. So basically in this case, the melting temperature will shift to the left with increasing pressure. Now you can think of apply the same thing like applied pressure on the vapor pressure of a liquid, and in that case you can think of assumptions like dissolution of, say for example, you have a pressurizing gas here. So this is your pressurizing gas and there is a liquid, and on the liquid there is this vapor because there is a liquid vapor equilibrium. So basically this space in the container contains the inert pressurizing gas plus the vapor. But see, we are neglecting this. The dissolution of pressurizing gas in the liquid is ignored, because if we do not ignore it, dissolution of pressurizing gas can change the property of the liquid completely or the nature of the liquid completely. Also, there is something called gas solvation or attraction of liquid molecules by gas phase molecules, which is again being ignored here. Right? Now, if the vapor pressure in the absence of pressurizing gas is Pi, if it is Pi, I want to see if there is a pressurizing gas, what happens to the vapor pressure. So, my applied pressure is delta P, my applied pressure is delta P, my original, the vapor pressure is Pi, right? Pi is my original vapor pressure in the absence of the pressurizing gas, and again, note the assumptions, right? Now, if you, in such case, at the liquid vapor equilibrium, as you know, mu liquid has to be equal to mu basically is the molar free energy of liquid has to be equal to the molar free energy of the gas, right? Again, it's a unary system. So, d mu, that means the change in molar free energy of liquid or the differential change in molar free energy of liquid has to be equal to d mu that of gas, right? So, basically mu liquid equal to mu gas. From here it follows, this relation follows. Now, d mu L is Vm dP, right? Vm liquid dP, and d mu G is Vm gas dP, right? Now, assuming the vapor to be an ideal gas, if you assume the vapor phase on liquid to be an ideal gas, often that's a valid assumption, you will see that Vm can be written as RT by P. It can be written as RT by P. So, if it is an ideal gas, then obviously Vm is RT by P, right? So, now you have the change in mu for the gas phase, which is RT by P dP, which is equal to change, because at equilibrium it is equal to the change in molar free energy or chemical potential of the liquid phase, which is equal to VML dP. So, basically you have VML, let us assume that VML does not change with, right, the molar volume of the liquid does not change with pressure. So, Pi and this is Pi plus delta P, right. It starts with Pi is the original vapor pressure, then there is the pressurized gas, and that as a result the pressure above the liquid has changed to Pi plus delta P. But here if you see, Pi has gone to P is basically, so Pi has gone to some value P. So, if I look at this, so basically, and P minus Pi is basically delta P. So, ln P by Pi equals to Vm liquid by RT delta P, right? Immediately you can see that. So, the pressure, you can write the change in pressure, change in vapor pressure. Basically here the change in vapor pressure equals to, is related to Pi times exponential, right? So, you have an ln, right? Here is a logarithm sign and here is this delta P, and we know that delta P. So, as you can see, the vapor pressure will increase by this amount, Pi times e to the power Vm liquid, that's molar volume of, it is proportional to the, so it will exponentially vary with the change in with delta P, and it is balanced by RT, right? Basically, if we assume the vapor to be an ideal gas. So, as you can see here, ln P by Pi equals to VML by RT into delta P. So, basically P equals to Pi e to the power, right, e to the power VML delta P by RT, right. This is how the vapor pressure will change when there is a inert gas pressurizing the liquid. Now, think of another thing. So, if you have a unary system, you can have a, you can basically map the stability, like where solid means in which ranges of pressure and temperature solid will be stable, at which ranges liquid will be stable, at which ranges, at what range gases will be stable. So, for example, you have these white lines, right? These lines, white, or you can think of this. So, these are the, this is a phase boundary, this is another phase boundary, and this is another phase boundary, and this marks the triple point where solid, liquid and gas can coexist. And these lines are basically phase boundaries which basically separate two phases, right? For example, this line separates liquid phase from gas phase, this line separates solid phase from liquid phase, and this line separates from solid phase from gas phase. And as you can see, the axis is a pressure temperature. See, we can use different types of diagrams like mu T diagrams and all, but this is called a pressure temperature diagram or a phase stability diagram, right? It gives you the stable phases, it maps the stable phases. But as you can see here, please note, this is an interesting point. If you have a single solid, like if this entire area occupies a solid phase, right? Solid phase is stable in this region. Now, in this area, only liquid phase is stable, and in this area, gas phase is stable. However, when three phases are, so basically a two-dimensional area is representing either a solid phase or a gas phase or a liquid phase, while a point represents an equilibrium between solid, liquid and gas, right? All of this, so this point is called triple point at which solid, liquid and gas can coexist. Again, this is a line, and along this line, solid and liquid are in equilibrium, right? Two phases. So basically the line represents two phases, point represents three phases. So for a unary system, a point represents three phases or coexistence of three phases, a line represents coexistence of two phases, and area represents existence of a single phase, right? So as you can see, TTR, PTR is the triple point, or sometimes I write it as, say for example, T3 and P3. So this is a triple point. So this triple point for a unary system basically means that point or that. So you can call this T, you can call this P3, and this you can call as P3, and this is the point. This pressure and temperature corresponds to coexist. So corresponds to a point where solid, liquid and gas can exist. But see, where the coexistence of three phases gives you a point, coexistence of two phases gives you a line. You can see the dimensionality in the phase diagram, and existence of a single phase is basically represented by an area. Why is that? So for that, to understand that, another thing, please note, say when Vs minus Vl is equal to 0. So this is something that you please try to find out why. I have given enough hint. So Vs minus Vl equal to 0, you see it is basically parallel to the y-axis, right? This phase boundary that you have between solid and liquid is parallel to the y-axis. However, when solid is greater than, means solid is greater than liquid, that is, this is the condition, that means volume of liquid is less than that of the solid, molar volume of liquid is less than the solid, then you see the tilt towards the solid, right? So you can see the phase boundary which is tilted this way, right? It represents some sort of a negative slope. On the other hand, when VL is greater than Vs, you have a positive slope, as you can see here, right? The phase boundary has a positive slope with respect to the axis, right? Again, this is the triple point, so I can call it P3 and T3. Right, so P3, and again here it is, this point is called P3 and let us call this T3, so that you don't get confused with the transition temperature. So this is the, so P3 and T3 represent this point, and this point is the coexistence point. But please have a note of the slope of the phase boundary between solid and liquid. When VL is less than Vs, then it is inclined to, it has a negative slope, and if it is greater than, VL is greater than Vs, it is a positive slope, right? And when VL equal to Vs, then basically, which is very rare, which is very hypothetical case, you will have a solid liquid boundary which is parallel to the y-axis. Now I will discuss why this area, why single phase is in a unary system. In a unary system means it's a single component system, right? Component number of components equal to 1. Number of components in a unary system. So if I think of number of components in a unary system, that is equal to 1. Now in such a case, you have the single phase existence is represented by an area, two phase coexistence is represented by a line, and three phase coexistence is represented by a point, right? You have seen that. Now, why is it so? So the answer lies in the equilibrium that we consider, right? In a simple system, what are the equilibrium we have considered? Temperature, thermal equilibrium. The temperatures have to be equal across all phases, and then pressures have to be equal, that is mechanical equilibrium, and the chemical potential of each species in each phase across all phases have to be equal. Like chemical potential of, say, if I have a component 1, then chemical potential of component 1 in phase alpha should be equal to that in phase beta, should be equal to that in phase gamma, if alpha, beta, gamma are in equilibrium, right? So now these basically give you this rule. This gives rise to this equilibrium, gives rise to this rule called Gibbs phase rule, and we can use this Gibbs phase rule to understand degrees of freedom and to understand the structure of a phase diagram, like PT phase diagram for a unary system, or structure of a phase diagram in a binary system or a multi-component system, right? So how does it come? It comes from this idea that if you have, say for example, let us look at a system of equations. So it comes from the idea of, if there are only cases, if I have to solve these equilibrium conditions, then I should have the number of variables which should be exactly equal to the number of equations. Then only I can exactly solve the equations. Other than that, I will either have an overdetermined system or an underdetermined system where I can have infinite solutions or no solutions at all, right? For example, if you have many equations but very few variables, then your degrees of freedom. So basically what I want to define here is the degrees of freedom in terms of unknowns or variables and equations, and we will consider linear equations here, right? We will consider for simplicity only linear equations. So you have, for example, let us look at this. So you have three variables x, y and z, and you have three equations which are linearly independent, and as a result you have three equations which are linearly independent and three unknowns or three variables x, y, z, and so basically this equation is exactly, so you will have a unique solution to this, right? So unique solution means degree of freedom, df, in short df, so or you can also call it f. So this is equals to number of variables minus number of equations. So in this case it is basically 3 minus 3, which is equal to 0. So here what you have is a unique solution to this problem. However, let us think of an equation like a set of equations like this: x minus y plus 2z equal to 7 and x plus y minus z equal to say 2. Now in such a case you have three variables but you have only two equations, so you have the freedom to choose either x or y or z. So you can choose some value of x, then you can solve it, and the number of ways you can choose the value of x is infinity. Again I can choose y, and again the number of ways to choose the values is infinity. Again for z the same. So basically in this case the system will have infinite solutions. So there is no unique solution, or there is no unique equilibrium that you can ascertain in this case. So basically here f, which is equals to m minus n, m is the number of variables and n is the number of equations, is basically 3, because you have x, y, z, 3 variables and 2 equations, which is equal to 1. So degrees of freedom is positive 1, it is not equal to 0, right? Now we can think of another system. For example, I give you a system like x plus y equal to 3, 3x plus 2y equal to 4, x minus y equal to minus 1, and then x plus 7y equal to 11. So I have 4 equations, I have 2 variables. Now think of this, you have 2 variables, so f equals to m minus n, m is the number of variables and n is the number of equations, so which is basically 2 minus 4, which is equal to minus 2. Now, as you can see here, I can take any two equations and solve, but it may not satisfy, the solution may not satisfy the third equation or the fourth equation. So, in such a case, you have basically in an ordinary approach, if you do not use a least squares approach, there is no solution to it, right? There is no solution. So, you have no solution. So, and degrees of freedom is -2, right? As you can see here. So, when degrees of freedom are 0, then only you have a unique solution. Otherwise, you do not have a unique solution. Either you have infinite solutions or you have no solutions. So, just apply the same concept. To a multi-component, multi-phase system. Now, multi-component, remember, we are talking about unary systems, but we will generally define a multi-component system, obtain the Gibbs phase rule, then we will apply to one component systems. But as an example, I can take one component in a multi-component system. One component is one of the systems and two phases. Now, if you have one component and two phases, then you have three equations: T alpha equals to T beta, P alpha equals to P beta, and mu alpha equals to mu beta, right, at equilibrium. Right? These are the equilibrium conditions, and this gives you three equations. But what are the unknowns? T alpha is unknown, T beta is unknown, P alpha, P beta. Mu alpha and mu beta, these are basically not, these are the energies themselves, right? Because it's a single component system, you cannot think of chemical potential of component 1 keeping other components constant. So basically you have only 4 variables, but you have 3 equations. So degrees of freedom, basically, so one component 2 phases, degrees of freedom is 1, right? If you have one component 2 phases, degrees of freedom is 1. Right, now think of two components and two phases. So you have two components, right, like 1 and 2 are the two components. Then you have this equation, right, the chemical potential of component 1 in alpha equal to chemical potential of component 1 in beta when alpha and beta are in equilibrium. Similarly for component 2, and then you have P alpha equal to P beta and T alpha equal to T beta. Now if you see, if I solve these two equations, what I basically get are the compositions, right, compositions of the alpha phase and beta phase. Now if you see, the compositions can be expressed in terms of mole fraction of component 2, and if it is so, mole fraction of component 1 in each phase can be obtained from the mole fraction of component 2, because x1 alpha plus x2 alpha equal to 1. Similarly, x1 beta plus x2 beta equal to 1, but we do not know x2 alpha, which is in equilibrium with the beta phase, right? x2 alpha equilibrium we do not know. Similarly, we do not know what will be the composition of B in the beta phase, which is in equilibrium with alpha phase, right? So we do not know that. So basically we do not, so there are two unknowns here. So we can see two unknowns here, not 4, because x1 plus x2 is equal to 1, right? In each phase, the component 1 and component 2, if it's a two component system, then the mole fractions of component 1 and component 2 in each phase will add up to 1, right? So if I know one, then I know the other, right? So basically the independent variables, so what are the independent variables? We have two variables here, we have T alpha T beta and P alpha P beta. So total 6 variables, and if you see, I have one equation, 2, 3, 4. So 4 equations. So if you have two components, two phases, you have two components and two phases, you have degrees of freedom which is equal to 2, right? Now think of one component, 3 phases, like the triple point, right? If you have one component, 3 phases, then you have mu alpha equals to mu beta equals to mu gamma. This gives you 2 equations. P alpha equals to P beta equals to P gamma, 2 equations. T alpha equals to T beta equals to T gamma. Equations are calculated by counting the equal to signs, right? So you have 1, 2, 3, 4, 5, 6 equations. So 6 equations. And what are the variables? Again, it's a single component system. So mu alpha equals to mu beta equals to mu gamma does not really give you any mole fraction, right? It's for us one component. So what are the variables? P alpha P beta P gamma and T alpha T beta T gamma. So basically you have 6 variables and you have 6 equations. You have degree of freedom equal to 0. As you can see, our triple point is unique and it's a unique point. So immediately you can see it is a unique point. Similarly, when I tell one component, 2 phases, I have a degree of freedom 1. 1 means basically a one-dimensional line, which is basically a one-dimensional curve, which is basically a line, right? Which is basically the phase boundary, which has 2 phase coexistence, right? Now, look at a more generalized description that you have like P phases. You have P phases and you have C components. So you have P phases and you have C components. Now, what are your equilibrium? We have for subsystems or phases, the same equilibrium applies if you are considering a simple system. So you have T alpha equals to T beta equals to, so if all of these phases are in equilibrium up to P, then you have T alpha equals T beta equals T gamma equals to up to Tp, and see you have P phases, so you have P minus 1 equations, right? Similarly for P alpha, P beta, P gamma up to P with superscript P, right? Because superscript P denotes the number of phases. So basically the total number of phases is, so this is phase P, right? This corresponds, this is phase P, this is phase gamma, this is phase beta, this is phase alpha. The pressures have to be equal, right, across all phases, right, when there is mechanical equilibrium, right? So then here also you have P minus 1 equations. Similarly, for each species, say if you have C up to C species like 1, 2, 3 up to C, then you have mu1 alpha equals to mu1 beta up to mu1 P, again P minus 1 equations. So for all components, if you have that, you have C components. So you have C times P minus 1 equations, and then these two equations are there. So these two rows, these two rows are also there, which will also have P minus 1 equations. So you have these two here. So you have these two and you have this. So 2 plus C. So total C plus 2 rows are there, and each row contains P minus 1 equations. So total number of equations N equals to P minus 1 into C plus 2, right? P minus 1 into C plus 2. Now C, you have component 1 up to C, right? Again, if you see any phase, x1 alpha plus x2 alpha plus x2c, xc alpha. So C components are there is equal to 1. That means one of the components, you can choose any one of the components to be dependent and all others are independent. So if you have that, you have T alpha to Tp, right? T alpha to Tp, these many variables, then P alpha to Pp, and then x2 alpha, x3 alpha, xc alpha, similarly x2 beta, x3 beta, xc beta, similarly x2p, x3p, xcp. So basically if I write it for phase alpha, the number of components are T alpha, the number of variables are basically T alpha, P alpha, x2 alpha, x3 alpha up to xc alpha. For phase beta, T beta, P beta, x2 beta, x3 beta, xc beta, right? So 2, 3, see I haven't included 1 because I have taken 1 as the dependent component, right? Now for phase P also you have Tp, Pp, x2p, x3p up to xc. So for each phase, the number of variables are 2 variables are here, and here this will be, if x1 is included, it becomes C variables, say 2 and C, but x1 is a dependent variable, so I am taking only the independent variables, so 1, 2 and all these C minus 1 variables. So you have 2 plus C minus 1, which is C plus 1 variables for each phase. But that means the number of variables for each phase, if you have C plus 1 variables for P phases, we will have P into C plus 1 variables. Now it becomes very easy. I can find degrees of freedom as number of variables minus number of equations, which comes out to be, if you just simplify this, C minus P plus 2. If temperature and pressure both are taken, then it becomes C minus P plus 2. However, for condensed phases, that is solid and liquid, often we ignore pressure, and if we ignore pressure, then the degrees of freedom will become F equals to C for condensed phase systems. That means there is no gaseous phase. The pressure volume work is neglected. In such a case, the F can be written as C minus P plus 1. We are not considering pressure as a variable at all. We are always assuming the pressure to be equal everywhere. Right? If it's a purely condensed phase system, that is, it contains only solid phases and liquid phases, no gaseous phase. Right? As soon as we have a gaseous phase, we cannot really use C minus P plus 1, but we should use C minus P plus 2, because in gases PV work is not negligible. right? So again, this is a diagram of a single phase. This is a single component system. So it's a single component system, and this single component system is pure water. And H2O can basically exist as ice, it can exist as water, it can exist as vapor. So please look at the negative slope between the ice water line, and also look at the phase boundary the degrees of freedom. In the phase boundary, ice and water are in equilibrium, that is, there are two phases, right? Ice and water are in equilibrium, there are two phases. So F equals to C. C is basically one component, 1 minus 2 plus 2. So 1 minus 2 plus. So basically you have one component, and you have two phases, and plus 2. So F equals 2. So at the phase boundary, which is 2 minus 1, which is equal to 1, right? So basically it presents a line. Therefore it is always represented by a line. Similarly, if you have a triple point, at the triple point F equals to, you have three phases. So minus 3, and you have one component, and plus 2. This is for a unary system. So this comes out to be 0. So triple point is uniquely determined. On the other hand, if you look at any single phase, then you have one component and only one phase and 2 degrees of freedom, right? You can basically specify in this area, you can specify one point where you have at that point you can define a pressure, you can define a temperature, right? So basically at any point, so basically if you have a single phase system, you can define independently pressure and temperature, right? Once you fix pressure and temperature, then degree of freedom will go to 0. Unless you fix pressure and temperature in a single phase region, it will not go to 0. So degrees of freedom will be 2, which represents a two-dimensional area, right? You have this area, right? Single phase is always, so in a unary system or a single component system, a single phase like ice or water or vapor, means where I am not talking about any coexistence, they will be represented by two-dimensional areas, because I can independently specify pressure and temperature, but once I have specified these two degrees, then my degrees of freedom becomes 0. Now I can uniquely solve the problem. On the other hand, along a line, let us look at a line. So you have this line where your two phases are coexisting. Now I can either choose a temperature. Once I have chosen the temperature, the pressure is automatically fixed. Once I have chosen the temperature, the pressure is automatically fixed. Now at the triple point, both pressure and temperature are fixed, right? You cannot have multiple triple points in a unary phase diagram, in a PT unary phase diagram. Now, one very important question, we have these slopes, but how do you determine, what is an equation that determines the slopes? What is the equation that determines the slopes? So, we move on to something called Clausius-Clapeyron equation. Again, the derivation is very simple. I'll quickly go through it. So, if you look at two phases, alpha and beta, which are coexisting, and this is the phase boundary, this is your phase boundary, then along the phase boundary, mu alpha, along the phase boundary, so this is your phase boundary, along the phase boundary, mu alpha equals to mu beta. And mu alpha and mu beta are functions of pressure and temperature, right? Mole number, because it's a single component, so it does not depend on the mole number. So d mu alpha is, as you know, d mu alpha is nothing but, and g alpha equals to g beta, and mu alpha is basically molar free energy. So, or gm alpha equals to gm beta, or mu alpha equals to mu beta. So d mu alpha equals to s alpha dt alpha, Pm minus S alpha dt alpha, right? dg equals to minus S dt plus VdP, right? So this is molar volume, this is molar entropy, right? This is also molar entropy of beta phase, this is molar volume of beta phase, right? This is for alpha phase, and you have dt alpha, dt corresponding to alpha phase, you have dt alpha, and you have dp alpha and dt alpha. Similarly, for beta phase, you have dt beta and dp beta. Now, at equilibrium, that is at the two phase coexistence, you should have d mu alpha equals to d mu beta. So you have minus s alpha dt alpha plus vm alpha dp alpha equals to minus s beta dp beta plus vm beta dp beta. But as you know from the mechanical and thermal equilibrium, that p alpha has to be equal to p beta equals to p, say some p, Okay, so P is say some value, right? P alpha equals to P beta equals to P, and T alpha equals to T beta equals to T. Now, if that is so, I can rearrange. So basically, what I have done is P alpha and P beta I have put as P, and T alpha and T beta I have put as T. So then I can write this as, so I have Vm alpha here, I have Vm beta here. So I can take Vm this way, right? So this becomes Vm beta minus Vm alpha dp, and I can take the S beta term this way, which becomes positive. So S beta minus S alpha dt, right? So basically, what is S beta minus S alpha? It is delta S alpha to beta, right? Delta S alpha to beta is S beta minus S alpha. This is delta V alpha to beta, right? So that's what I'm writing. So Vm beta minus Vm alpha is delta Vm alpha to beta dp equal to delta S alpha to beta. So this is the transformation dt. So now you can see, now you have this pressure. So you have the pressure and temperature axis, right? Pressure and temperature as the axis. Pressure, temperature axis. So del P del T, right? Del P. So this curve, if you look at the slope of this curve, right, is P as a function of T, right? How P changes as a function of temperature is what is plotted. Now, as you can see, the slope of this curve is given by, at any point, is given by del P del T. And del P del T or dp dt is nothing but delta S alpha to beta. So this is the entropy of transformation, and this is the molar volume of transformation, that is the change in molar volume during transformation from alpha to beta, and this is the entropy of transformation. Remember again, delta S alpha to beta is the same as delta S beta to alpha, only there is a negative sign. Similarly for delta T. So these equations are called as Clausius-Clapeyron equation. Now these equations can be used for all these boundaries like solid liquid boundary, for liquid vapor boundary and solid vapor boundary. Say for example, if you use it for the solid liquid boundary, then you are considering Tm or melting or freezing point. Tm again is a function of pressure, right? Tm can change the function of pressure, we already know, and we are looking at solid to liquid, which is basically melting, where heat is absorbed, right? Melting means heat is absorbed, and freezing means heat is evolving, right? And you have mu alpha equals to mu beta, and you have also G alpha equals to G beta, which means H alpha minus Ts alpha equals to H beta minus Ts beta. Again you arrange, so delta H alpha to beta equals to T delta S alpha to beta, and the transformation temperature, TTR, that is the transformation temperature, is nothing but Tm, right? The melting point. So if you have that, dp dt becomes this equation, right? Delta S alpha to beta to delta Vm alpha to beta, which can be represented, means basically since delta H alpha to beta is Tm delta S alpha to beta, I can write delta S alpha to beta equals to delta H alpha to beta by Tm, right? So basically this becomes delta H alpha to beta by T into delta Vm alpha to beta. Now this T is nothing but Tm, right? Now let us think of this. This is a general Tm, right? This is a Tm, which again is a function of this melting point of this transition temperature. This transition temperature is a function of P and T, right? It can change as a function of pressure, it can change as a function of means basically if I change the pressure, basically if I am think of this, if I am changing pressure, automatically I am fixing temperature, right? If you look at Gibbs phase rule, so basically Tm can change as a function of pressure, right? And so how does the T change? So let Tm 0, let us look at this, let Tm 0 be the melting temperature at pressure P0. Now let Tm be the melting temperature at pressure P. Now if delta H alpha to beta and delta Vm alpha to beta do not vary much, right? We assume them to be nearly constant, but we can actually assume, we can basically think of temperature dependence, but if we ignore the temperature dependence for a while, if you do not ignore, then all this delta Cp and all this stuff will come in. But if I want to ignore for the time being this delta H alpha to beta and delta Vm alpha to beta as a function of temperature, the temperature dependence is ignored and we are assuming it to be constant independent of temperature, then we can basically easily integrate this equation. So you have P0 to P dp, right? So basically this guy will come here with dp, and this guy will come there, and there is a T term that is there, so dt by T will be there, and you have this, right? So this T will be there, dt by T, and this will be separated, and there is a dp, right? So there is dp, there is no pressure that has to, so you have delta H alpha to beta and this one, so these guys remain as it is here, and you have dp here, and dt goes here, and this is dt by t. So this is dt by t, and dt by t is nothing but dl and t. It is nothing but dl and t, right? So you have dl and t, and you have this Tm0 as the melting temperature, right? Tm0 is the melting temperature at pressure P naught, and so Tm naught is the melting temperature pressure P naught, and at temperature and at pressure P it is Tm. Then basically we can write P equal to P naught plus, see, this is, we are assuming that delta H alpha beta and delta Vm alpha beta do not change with temperature, right? We can use their temperature dependence, or functional dependence of temperature can be used. Then we will have to use delta Cp and how it varies with temperature. But if we ignore that for time being, this guy is constant, right? This guy basically I know, if once I know this, so I know this term, then I have P equals to P naught plus this term into ln, right? Because dln t, right? dt by t is nothing but dln t. So which is basically, if I integrate it, is ln tm by tm naught, because tm naught and tm are the integration limits, right? This is the lower limit, this is the upper limit. So this is ln tm by tm naught, right? ln tm by tm naught, and this term. And so if tm by tm naught is small, then ln tm by tm naught, again I am using the same trick. So ln 1 plus tm minus tm naught by tm naught, which is approximately equals to, so this is approximately equal to only the linear term, right? The other terms will be anyway smaller, right? Because it is whole squared, whole cubed, and so on. So basically I can think of this tm minus tm naught as delta tm by tm naught, and so we can just write this as P equals to P naught plus delta H alpha to beta delta tm, and there is a tm naught delta Vm alpha to beta, right? So basically this is for a solid liquid boundary. So we can easily find out how to or determine the solid liquid boundary equation. Similarly, we can do it for a liquid vapor boundary, where you have alpha to beta transformation, evaporation and condensation, and so basically alpha is liquid and beta is vapor. Evaporation will give alpha to beta, and condensation will give beta to alpha. And we can assume that for gas, the molar volume of gas is much larger than that of the liquid. So then we have this equation dp dt equals delta H vaporization by T delta Vm vaporization. So if you assume the vapor phase to be an ideal gas, then you can write Vm beta equals to RT by P, which we have done. So basically if we follow this equation, you get something like dln P equals to delta H vaporization by R dt by T squared. So I will basically continue in the next class, in the next week. I will finish this. I will finish this Clausius-Clapeyron equations, but you can quickly go through it and you can understand it. So this is for the liquid vapor boundary. Similarly, we can do it for a solid vapor boundary. And for triple points, how to determine, you basically, if you know the, so for example, if you are looking at a transformation from alpha to gamma, you can subdivide it into gamma to beta and beta to alpha. So I will continue all this discussion in the next week's lecture. Okay, so thank you.